This lesson is on Chapter 3, Part A, on radicals. Radicals are a type of number. They're numbers that use square roots, such as maybe the square root of 2, or the square root of 3, or the square root of 5. You might wonder why I'm skipping some numbers. What about the square root of 1? Well, the difference between the square root of 1 and the square root of 2 is that the square root of 1 can be written as an integer. I don't need a radical sign because the square root of 1 is equal to 1, right? 1 times 1 is going to give 1 back again. So the square root of 1, sorry about that, the square root of 1 is equal to 1. I changed colors by accident. Okay. Maybe it's easier to think about that in terms of the number 4. The square root of 4, we all know, hopefully, is equal to 2. Because 2 times 2 gives us 4. So the square root of 1 and the square root of 4 can be written as integers like this. So they're not really radicals. The difference here with these numbers, if I actually try to figure out what number times itself is going to give me 2, I end up with a big long decimal, a non-repeating, non-terminating decimal. So not like something like 0.33333, that would be repeating. Or something like 0.3 repeating, that's not what radicals end up being, or 0.15, that terminates because it stops, there's no decimals after that. So these are not radicals. Radicals always end up being long, big decimals that never stop, go on forever and ever, and never have a pattern, just like pi, right? They're irrational numbers. So those are the kinds of things we're going to deal with in this chapter. Now, something interesting about radicals like this is if you multiply them by themselves, then you get the number under the radical sign as an integer. So square root of 3 times square root of 3 is equal to 3. That's kind of a hard thought to get used to, but it's really important. Maybe if we compare this with doing it with square root of 4, it will be a little easier to understand. So let's do square root of 4 times square root of 4. Well, the square root of 4 is 2, and then I multiply it by another 2 because this square root of 4 is also 2, and that equals 4. So here you can see that the square root of 4 times the square root of 4 is equal to 4. Another way of thinking about it is square root 4 times square root 4 is the same as the square root of 16. I can simply multiply the two radicals together. And we know that the square root of 16 is equal to 4. So over here too, I can think about this as square root of 3 times square root of 3 being equal to the square root of 9, which we know is 3. Okay, so multiplying a radical by itself gives you the number under the radical as an integer. So let's do some examples. If I take something like square root 6 and square it, squaring a square root, they kind of undo each other. They're inverse operations. If I take a square root and get the square root of 6 and then I square it again, I will get 6 back again. You could try it with your calculator if you want. Pause the video and try square root 6 and square it. You should get an answer of 6. Another example, even when it gets more complicated, the same thing applies. So here I have a fraction, 1 over the square root of 2. The radical is in the denominator. And when I square that, that's like doing 1 over square root 2 times 1 over square root 2. So multiplying across the top, 1 times 1 is 1, and square root 2 times square root 2 is 2. So 1 over square root 2 squared is the same as 1/2. Okay, let's try another one, getting a little bit more complicated. If I take a combination of an integer and multiply it by a radical, and then square it, this is the same as 2 times the square root of 3 times 2 times the square root of 3 This is all the same operation. Just because I've written these next to each other doesn't mean we aren't doing something in between. This is actually the same thing as 2 times the square root of 3. When I write the numbers like this, there's an assumed multiplication sign here that I don't actually have to include. So because this is all the same operation, and multiplication can be done in any order, I can actually change this to 2 times 2, and then times square root 3, and times square root 3. So I can change the order in which I multiply it, and that means I can put these two 2's together, multiply them together to get 4, and I can multiply square root 3 times square root 3 to get 3. Now I do need a multiplication sign because it's not a radical anymore. It's an integer, and I have 4 times 3 as a final answer, which is equal to 12. So 2 square root 3 squared is equal to 12. Try it in your calculator. You can put in 2, and then you have to hit the square root button to make the sign, and then put a 3 under it. Then put an arrow, a cursor, to get out of the radical sign before you hit the multiplication sign. And write another 2, open up the radical sign again, the square root button, put a 3, and then hit, and probably to get out of the radical sign again, you might just be able to hit enter from that point. Or if you want to do it completely with the square root sign, then you can put a bracket, 2, the square root button, 3, the cursor key to get out of the radical, end of bracket, and then your square button. I think it's got a hat with a 2 on it or something like that. Okay, and see if you get 12 out. You should. Okay, let's do some more examples that get a little bit more complicated. We can introduce a negative sign. Negative 2 times square root 5 times 3 times square root 5. Just like in the last example, because this is all multiplication, negative 2 times square root 5 times 3 times square root 5, I can do it in any order I want. So I could do negative 2 times 3 times square root 5 times square root 5. The negative 2 times 3 makes negative 6, and the square root 5 times square root 5 equals 5. And so as a final answer, I have negative 30, negative 6 times 5. Okay. You don't necessarily have to show all of your work here. I'm doing this so you can follow what I'm doing, but do at least show this step and this step in your works, even if you don't show this part. You can go straight from negative 2 times 3 is negative 6, and square root 5 times square root 5 is 5. Multiply them together to get negative 30. Okay, that will help you with A.1. If we're going to move to A.2, we will start adding and subtracting radicals. So here's the first example. 2 square root 3 plus 5 square root 3. If we think of this square root 3 not as an actual number, but as a little bit of something, you might be able to see a comparison to working with algebra. If you think of this square root 3 as maybe an x, some variable, then I can also write 2 times that little bit, that variable, and then I also have 5 times the same variable, because that's square root 3 as well. So this is going to be 5 times x. And the same rules that apply to bits of algebra like this are going to apply to adding radicals. If I have the same radical, here square root 3 and there square root 3, I can simply add the coefficients together. Remember, the coefficient is the number in front of the letter. So this is the coefficient. And I'm going to add 2 plus 5 to give me 7x. And that's the same process when I'm working with radicals. So I think of 2 square root 3 plus 5 square root 3 is going to be 7 square root 3. And I can't actually simplify that any further. That is as simple as it goes because square root 3 is going to be a big long decimal. When I multiply it by 7, I'll get another big long decimal. So we're just going to leave it like that. Subtracting works the same way. Let's look at an example. 5 square root 3 minus 6 square root 3. And just ignore the square root 3's for a moment and look at the coefficients. 5 minus 6 is going to be a negative 1. Just like in algebra, I don't have to write the 1, I'll just have a negative. And then, of course, I have the square root 3 yet, so negative square root 3. So think of these little radical bits as like terms, and then follow the same rules for algebra where you only collect like terms. If we make this expression a little longer, we can start with 5 square root 3 again. But let's take a different radical. Let's take 2 square root 5. And now we can subtract something off of it and add something and something else. Okay, when I'm adding things like this, I have to look for like radicals. So I can't just add all the radicals together. It's very tempting to say, okay, why doesn't this make 7 square root 8, these two right here? Right? 5 plus 2 is 7, and square root 3 plus square root 5 is 8. So why not 7 square root 8? It doesn't work like that. Remember, this isn't just a 3. It's actually 1.7 something or other. It's a big long decimal. And I'm first multiplying it by the 5. Same thing here, square root 5 is 2 point something, and then I'm multiplying it by 2. So by the time I do all of that, the numbers have changed completely. So you have to be careful. Don't just add radicals together. We look for like radicals. So this one can be put together with this one. I'll use a different color to show this one, which is square root 5, can be put together with this square root 5 here. Take the signs along with the radical that comes after it. The 3 doesn't have a radical. So that's like having a constant number with no variable, right? Think of your square root 3's as x's and your square root 5's as y's. This is a constant number that doesn't have a radical, so it's just going to stay by itself. So 5 square root 3 minus 2 square root 3 is going to be 3 square root 3. And 2 square root 5 plus square root 5 is also going to be 3, but square root 5. So in the end, that will be a bigger number than this will. And then plus 3. And that's as far as we can go in terms of adding things together. Because there's a 3, a factor of 3 in each one, I could actually factor something out, but we'll leave that for now. Factoring isn't necessarily simple, it's just another formula. So that's the final answer here. And that one's for there. Okay, that's it for this lesson. Good luck finishing the work for section 3A.